Roman numeral 2 is on graphing logarithmic functions. Okay, it says to graph the functions in the same rectangular coordinate system, f of x equals 2 to the x, which I have already plotted here. We've looked at this one before. And then we want to graph the logarithmic function g of x equals log base 2 of x. Notice that these are inverses of each other. The base here is base 2, base here is the same, so I could convert between these two forms. So I went ahead and graphed f of x, okay, which we've looked at before. The inverse to this, the logarithmic function, remember with your inverses it means that you could just interchange your x and y values. So where I have negative 2 1/4, I would have 1/4 negative 2, and then 1/2 negative 1, 1 0, 2 1, 4 2, and 8 3. Okay, because by definition of an inverse, it means that those x and y values are just interchanged. So if I want to plot those values now on my graph, if I say x is 1/4, then my y value is negative 2, 1/2 negative 1, 1 0, 2 1, and 4 2, and 8 3, which I would have to go out a little further to get that one. But this would be the shape of my logarithmic function, log base 2 of x. Okay, as you can see, there's some symmetry here. They are symmetric, or kind of reflections of each other. Okay, well, notice, remember with the exponential where we had a horizontal asymptote at y equals 0, we have a vertical asymptote at x equals 0 with the logarithmic function. Okay, what do you think the domain of this function would be? Okay, we know the domain of the exponential is all real numbers, but the domain for the logarithmic, it's never going to cross over this x equals 0. So it would be from 0 to positive infinity. The range, because this will continue to go down, continue to rise, will be all real numbers. So just the opposite, or just the reverse of what we had for exponential. There's a list of characteristics in your book, much like what we looked at for the exponential. If you go to section 3.2, you should be able to find this chart in your ebook through My Math Lab. Again, it repeats what I said about domain and range, just the opposite. The domain of a logarithmic function will be from 0 to infinity. The range will be all real numbers. It says the graphs of all logarithmic functions of this form will pass through the point 1 0. Okay, so the x-intercept is 1, because f at 1, log base b of 1 would be 0. You know, b to what power would equal 1, so b to the 0. There is no y-intercept. If b is greater than 1, then you will have a graph that goes up to the right and is an increasing function. If b is between 0 and 1, you'll have a graph that goes down to the right and is a decreasing function. We say that the graph of the logarithmic function approaches but does not touch the y-axis, so we have a vertical asymptote at x equals 0. So those are some properties and characteristics of the logarithmic function that you should be familiar with. As far as the domain, because we say that it has to be from 0 to infinity, if you're just given the function like number 12 and asked to find the domain, you would take your argument x plus 9 and set it greater than 0. Okay, that has to be greater than 0. So that would mean that x is greater than negative 9 if I solve the equation. So my domain would be from negative 9 to positive infinity. Okay, that fits right in with what we've talked about with transformations. Okay, this would be a transformation of my base function. 9 being added to the variable means that my graph would be shifted to the left 9 units. So that would bring it over from being at 0, 1. It would be over 9 units, and so we would have a different domain. Okay, so this is one example of how you may be asked to find the domain on your homework problems.